Hello again. I'd like to, in this next lecture, give you an overview of applications of diffraction measurements in materials characterization, and just give you a highlight for the kinds of questions X-ray diffraction is best suited to answer. Realize, of course, this is a very incomplete discussion of this area, and the interested student would be well served to more deeply study the relevant literature, or maybe even take a specialized course that extensively treats diffraction-based characterization methods. Should it be a critical component for your future research. So anyway, with that, let's jump right in. So what is X-ray diffraction? Well, there's a lot of nice information like we can put up here. That is, it's a scattering phenomenon. X-rays pass through a crystal, and the crystal modifies the trajectory of those X-ray photons in interesting and useful ways. But how these modifications happen provides a tool that can be used to characterize a material based on its crystallographic structure. That is to say, based on the position of all the atoms within the solid. And this is the kind of information that's used intensively by chemists, physicists, material scientists, earth scientists, basically, if you care about the structure of something, and for cases where that structure has long-ranged periodicities associated with it. In point of fact, X-ray diffraction is one of the best techniques, and sometimes, the only technique that can be used to deduce information about, how atomic arrangements exist within a solid material. And of course, it has a very famous history, like the famous X thing. This is not, X for the X-Men, but rather this was the X-ray diffraction pattern taken by Franklin that ultimately led to the solution of the structure of the double helix, the double helical structure of DNA. And of course, was the subject of a very, important award of the Nobel Prize, for which Franklin did not share. But although she had, I think, died before that prize was awarded. Okay, so what's it used for? Determination of a crystal structure, basically, and more essentially, to measure the unit cell dimensions and symmetry and atom positions within a crystal, to identify materials, right? So I can either determine where the atoms are in a solid, or I could use it as a fingerprint to tell me what the solid is if it corresponds to, in fact, a known a compound for which diffraction data has been recorded. The composition of mixtures, determination of grain sizes, strains within those crystallographic structures, and in crystallographic orientations, and like typical samples would be single crystals, powders, films, materials of diverse form. Now, I think it's really important to lay out a case where crystallographic information is really important. So we mentioned in previous lectures words such as polymorph, and what do I mean by a polymorph? Right? Well, I can imagine cases where I determined the composition of a substance, but still I don't really know enough information about it. So here's a case where I could determine elemental structure, and it is in fact a composition. One zinc atom, one sulfur atom, repeated ad infinitum in some way. But in point of fact, those could be arranged in very different ways. And so here's depicted two very different crystal structures of this simple mineral, zinc sulfide. One being characterized by crystallization within a cubic unit cell, and the other being one that adopts a hexagonal unit cell. And that's another word that we just invented, right? The word unit cell, which is basically the smallest volume of space, in which you can sequester all the essential atoms, but which, when repeated ad infinitum, generates the entire, full extent an extent of the crystalline habit. So you can see in those two cases, the diffraction patterns measured in a particular way, which we'll talk about, differ very much. So if I didn't know, in fact, what form of zinc sulfide I had, a diffraction measurement would, in fact, give me a very good way to determine that part of a structural attribute. So let's look at the history. Obviously, we start with the point where there was a discovery, and of course, Röntgen is well known. A beautiful picture of, I believe, his wife's hand and wedding ring, and kind of a scary picture because they were probably pretty nasty X-rays. They didn't realize how dangerous they were. But of course, Nobel Prize was awarded for that. Von Laue discovering the fact that in essence that crystalline solids were an effective grading for light of the wavelength of X-rays, and prove the particle wave duality of it. That was a Nobel Prize. Lawrence and Bragg for developing the method of X-ray crystallography, and actually using it to solve the structure of zinc sulfide, diamond, and other materials. So, for example, Nobel Prize in 1915, and since then many extensions and tremendous and powerful extensions. For example, it used to be an absolutely almost unbearable effort would be required to do a data analysis. So if a unit cell had 20 atoms, it could take you years to solve the structure. But now you can do relatively massive unit cells in very little time. And that's because the computational parts of data analysis are now very much more advanced, and the methods for doing data analysis are much more advanced. So this has been a constantly evolving field, and of course the power of what can be done has increased enormously, and we'll see some examples. So what are X-rays? X-rays are electromagnetic radiation, right? And I like that. It's an electric field and a magnetic field chasing itself through the firmament, for eternity in a lossless way. And but it's also a particle, with a photon energy E. So it's a wave, an electromagnetic wave with a wavelength and frequency, and it's a particle with an energy E, given by the velocity of light and wavelength and Planck's constant. Okay, and the thing about electromagnetic waves is that it interacts with the electrons, and it's nice to know what's the part of the story. So like we get a crystal structure not because it figures out where the nuclei are, but rather it figures out where the area of electron density surrounding the nuclei are, and hence the position of the atoms themselves. So that's a little subtlety. X-ray sources are an area where there's been a lot of design. So typically in the laboratory setting, you'll use something that kind of looks like what's shown on this slide. Namely, that there's a filament, right? So, I think it's a really, good thing to, sort of get a first order feeling for, how do you get your hands on an electron? And so, the thing that people say is that you boil them off, right? And really what this is called thermionic emission. You heat a filament to very high temperatures, and when that thing is heated, if you take that filament and then bias it at very high potential, so like for example, the bias between the filament and the target, being of the order of 50,000 electron volts, you will pull off a number of electrons and accelerate them to fairly high energies, and those electrons will then slam into the target, and in that collision they'll emit X-rays for reasons that we discussed in earlier lectures. And the reason why you heat the filament is that the number of electrons that you get off goes up with temperature in a rather important way. So all filament-based devices, and for any guitar players in the audience, if you have a tube amp, the same thing. That's why the tubes in the back of your amplifier glow, because you just got to get your hands on those electrons. Okay, so the X-ray comes off in a spectra, and it has like two components in it. It has spikes, and it has basically a background, so-called continuous radiation, and in the background, this broad profile is called, actually more properly called Brimstrahlung, which is the continuous background, and it basically is the X-rays that come from all the ways in which electrons have inelastically changed directions and trajectories, etc. Right, so it's a really broad spectrum of X-ray wavelengths, and the diagram shows some examples of like how that might happen, based on different ways that electrons have been scattered from an atom. But this other kind of X-ray radiation comes from those events that we mentioned, where an electron comes in, where a photon comes in and actually knocks an electron out of a particular bonded shell, and then stuff happens from there. So for example, incoming electron knocks out an inner shell electron, and an empty site is filled by an electron dropping from a higher shell. Right, we saw that in our discussion of XPS and Auger electron spectroscopy, and that difference in those energy states has to be carried away either by the emission of an Auger electron or by the emission of an X-ray. Right, and so depending upon where that electron drops in from, we identify different kinds of transitions, alpha, beta, and in both cases they would give rise to X-ray fluorescence amongst other de-excitation processes. But these X-rays would have characteristic wavelengths associated with the energy differences shown for these alpha and beta processes. Right, and they correspond to the spikes that are seen in the so-called characteristic radiation peaks. So a typical like XRD experiment might be done with with a copper anode, and the line that you might use because it's intense would be copper K alpha, which has a wavelength that's appropriate for measuring interatomic distances, of the order of 1.54 angstroms. Okay. So interactions of X-rays with crystals, crystal structure, three-dimensional periodic arrangement of atoms in space. This shows, a common crystal, sodium chloride, a fairly reasonable size and the number of atoms that are present in the unit cell. Okay, and I think the thing that's interesting to note that sodium chloride was a structure that was solved in the original research leading to the award of the Nobel Prize, and the kinds of structures that are being solved now, right? Is so for example, the so-called red dwarf virus that's shown here, it's infamous because it's bad for you, right? But it's also an infamous kind of material for trying to do a crystallographic structural determination, because the ordered habit of all the atoms present in this object, basically correspond to a unit cell volume that's 3 million times the size of the unit cell of sodium chloride. So that's a lot of atoms to figure out where they are. But this is the kind of things that can be done, or at least approached through the current capabilities of measurements of this technique. So the interactions of X-rays with crystals are in two forms. Yeah, and the one that we care about for diffraction is the coherent scattering, and that is the event that leads to a change in the trajectory of the X-ray, the propagating X-ray, happens without an energy loss. And that is that the photon coming in and the photon going out have exactly the same energy. Right? There's no energy loss mechanism. And of course, there's another process, incoherent scattering, so-called Compton scattering, and that's where the scattering processes are inelastic, and the outgoing photons have lost energy, but they're not the foundation of diffraction. It's only the parts that scatter coherently and elastically that give rise to the things that we analyze, within a conventional X-ray diffraction experiment. So the way to think of this is that that the incoming X-ray is a plane wave, right, which interacts with the scattering center, and that every electron / atom, right, because the electrons are kind of like following where the atoms are, in a structure, act as a scattering center, and it's a source of a spherical wave that has the same wavelength as the incoming plane wave that is the photon. All right, and that gives rise to characteristic interferences, right, which are actually shown in the animation. And so if we have two scattering centers, we have a series of waves that come out from those scattering centers, and you'll notice that we have a more complicated set of interferences, both positive and constructive, right, which correspond to the scattered components coming at us ad infinitum, right? And so when we have lots and lots of atoms, right, we get positive interferences, right, and they add up, and they with more amplitude. And we have we have negative interferences in crests and troughs that are offset and cancel each other out, right? And there's nothing left. But the thing is, when you have lots and lots of atoms, there's lots of ways in which the scattering events cancel each other out. So it turns out that lots of scattering centers, lots of things canceling, but few special high symmetry things that do not, right? And that gives us the information that we analyze in diffraction, according to. And so to repeat that, there's special combinations of wavelengths and incident angles that allow coherent constructive interferences, right? That comprise what's diffraction, and these specific forms of constructive interference, when analyzed in terms of these angular attributes and whatnot, can be analyzed according to a very fundamental relationship, and that is Bragg's law. That relates dimensions of periodicities and wavelengths, periodicities and wavelengths, and the angular attributes that the scattering is done off of a crystalline material in a way that actually begins to let us define something related to the crystalline habit of a material, right? So, Bragg's law is the fundamental revealed form of truth in this method of analysis, right? And so we can look at Bragg's law from a geometric perspective and think about how it is that this incoming waveform is scattered off of the corresponding periodicities associated with the crystalline habit. And you notice, for example, there's a in this two-dimensional representation, there's a particular symmetry of atoms that are shown, with a corresponding spacing. And an arriving a waveform done in such a way that the phase relationship is maintained the way it's supposed to be. So, for example, you notice in the components in red, between the arrival of this atom and leaving it, right? That and as defined by a vector along that particular scattering angle, that's exactly 1 unit of wavelength lambda. Okay, and to kind of look at how that all plays out, that the X-rays are in phase, right? There's a characteristic distance that corresponds to this so-called D spacing, right? And there's a characteristic distance that corresponds to the wavelength. That at that particular angle, that one characteristic wavelength actually then has a spatial offset that's distance d from the scattering plane 1 unit up at that characteristic d spacing. Right, and so that's like the fundamental attribute here. That that in point of fact, these path differences must correspond to one wavelength or multiples of one wavelength. So lambda or n lambda. Okay, and the despacings can be related to the nature of the unit cell in very characteristic ways. So if you go into the details of X-ray diffraction and things that would become the point of focus in a more extended treatment of this subject would be how in fact we analyze the crystalline, the known existing, the known forms by which crystalline solids form. And there's only it's a large number, but there's only there's a finite number of symmetry elements that exist, and a finite number of crystalline forms that exist, and symmetry systems that enable crystallographic forms, and some are more common, others are less common. Some are relatively simple, and some are just wickedly complicated. Some of the important examples are shown here. For example, the description of the unique set of integers, and which would actually characterize particular directions and symmetries within the crystal system. And here indicated for cubic, tetragonal, and orthorhombic components. So we can in fact get information about these kinds of symmetry attributes from the things that we would measure in an X-ray diffraction experiment. So that's kind of the simple story of it. Because the peak reflections reflect the unit cell dimensions, it's easy task to refine the cell, right? So if we have information as a function of lambda as a function of angular attributes, etc., right? We can assign these Miller indices to each peak, and we can gain accurate information from the unit cell, like all the underlying symmetry elements, and minimize this information to get the convergence at the best description of the attributes of this disposition. And in fact, that's how we would resolve a structure, by looking at all the characteristic reflections and using that to come and assign the values that actually define the symmetry elements for a particular spacing that's seen in the diffraction pattern. Okay, so powder X-ray diffraction. This is how you will normally do it. Some of you may actually be inorganic chemists, and then you'll do, I think a lot of my friends in that world, do a lot of single crystal X-ray structure work, as their penultimate analytical tool. It's not something that I tend to do, because very few of the things that I do, with the exception of work with semiconductors, is typically it doesn't involve single crystalline materials. Semiconductors, that's not the case, because we're doing electronics. But for the kinds of materials we use for structural purposes or whatever, they're much more complicated. They maybe contain amorphic components, they're component mixtures, etc. Right, and in fact, may incorporate things in powdered form, and where powders have vastly different sizes, and that all has an impact on what you would be able to measure and see with X-ray diffraction. So powder X-ray diffraction probably will be the more important and common protocol that you would use in a measurement in a material-centric context. So the diffractometer, basically lets you do a number of things. This is a so-called Bragg-Brentano geometry for an instrument, and it lets you control the wavelength, because basically you select what the X-ray source is, whether you're going to use for example copper K alpha, tungsten, whatever, there'd be a molybdenum K alpha, there'll be a variety of different wavelengths you could select, which you would select based on attributes that would be important for the kind of system that you're trying to analyze. But that's a choice that you get to make, and you get to control the angular attributes. Basically the position of the X-ray source and its disposition relative to the sample, and the disposition relative to the detector, right? And so all these angular features, right, are things that you would pick as a way of doing this experiment, and so for here, the entering and scattering angles are specified, and that's just a picture of one of these type of instruments, in our analytical facilities at Illinois, and you likely have similar things here at KTH. Okay, so we choose the incoming and outgoing angle, and thereby the diffraction planes that we're going to assess. And so here's a hypothetical sample, which is actually a single crystal, and if I did a placement of this single crystal in such a way that I come in for a reflection event that corresponds to this particular crystallographic plane, then in fact the only scattering I would see, would be that corresponding to that particular crystallographic plane, right? That particular underlying spacing. I would miss everything else about this sample, if I did that. So, if we want to know, every possible, diffracting orientation within this crystal, I could either rotate the crystal, with respect to beam, or I could actually do a measurement on a powder in such a way where, the powder would present smaller crystals, but with every possible orientation, so averaged over every azimuth, and then what I would see, would be a more complicated diffraction pattern, right? So this thing would have to be ground up into small sizes, and ideally of the order of a number of microns, and in such a way that by their nature the grains orient randomly in the sample holder, and that's what we would call powder diffraction. Right, so here's what such a diffraction pattern would look like. It's basic, and it's plotted here for 2 theta. That's a kind of angular dependent scan that we would do in this class of measurement, where we're looking at intensity as a function of this angular attribute of the measure, right? And we notice here that there's lots of peaks, and they're against the background, and we might extract that background as part of the measurement, and then we go ahead and look at the peaks, where at a certain angle with certain intensity resulting from these positive interferences, we see things that correspond to particular symmetries, but the question remains, I can read those angles out, right? Obviously, very very accurately, but like what I need to know is like what is this stuff, right? That's the fundamental question. All right, I now know that this sample is crystalline, but what is it? Okay, so typically what you do is first and foremost you got to reduce this information to something that's understandable, right? And the thing that's understandable is the characteristic distance of the lattice spacings that are involved, and so you start obviously with the fact that I used a particular anode for the measurement. This was done with cobalt K alpha. It has a wavelength of 1.7889 angstroms. You need to know that, and then you can go ahead and look at these angular attributes, right, and the relative intensities, and actually calculate the spacings for the reflections for all the peaks, right? And here's for the first 9, all right, and according to their relative intensity, right, analyzed according to the Bragg relationship. And you notice that there's a set of numbers there, right? 5.07 angstroms, 4.98 angstroms, 4.89 angstroms, 3.68, 3.16. This is a fingerprint, right? This is like a fingerprint that says something about the kind of stuff that's here, and people that are really skilled can look at that, and they probably already know, exactly, what kind of symmetry, has to be present for this to be true, if in fact it was a single phase component. But for those of us who don't think like that, the good news is that there's databases, and any instrument that you would use nowadays is going to be hooked to a computer, and definitely, since your data is hooked to a computer, your computer can be hooked to the corresponding international databases that would tell you, what it is that you're looking at. Because and frankly, there's software packages that do this very powerfully, and the thing is that there's there's way more than 200,000 known structures that are currently in the database, right? So you can really search a lot of compositional and structural spaces just by the analysis of for example, the strong features that are seen in the diffraction pattern, right? So there's a particular mineral structure, right, that actually fits this data very well, so that you would know not only the fact that this was an aluminum silicate, right? Sodium, potassium, calcium, aluminum silicate, right? But in point of fact, it's a particular crystallographic form of a well-known mineral, and this works well as long as the peaks are strong and the database actually has good stuff in it, right? So databases can be searched by characteristic despacings, right? So that shows you it's select, distance is the searchable parameter, and it's like a fingerprint, right? And so we can go ahead and look at that and search program to identify the composition of a sample, even including mixtures. Like, so for example, I'll just click through this and you'll note in these slides, right, that there's a number of different peaks being assigned here, right, that are actually, corresponding to reflections coming from a fairly complex a mixture of materials: iron oxide, zirconia, an iron titanate, and a rutile form of TiO2, right? And that's an example of a fairly, complex, multi-phase, multi-compositional, mixture of substances, being actually characterized in terms of the quantity of material that's present. And in point of fact, right, it's not only identities, but like if we look at different mixtures, you can kind of run through this and from the known standards actually then deduce, what is the elemental composition, within the sample. So not only what phases are present, but, what amounts. So like, for example, varying the rutile composition from 5 weight percent to 60 weight percent, and analyzing the spectra, right? I mean, the diffraction patterns in these powder diffraction experiments, right, to actually show you that the weight compositions are actually varying in the way shown, right? But there's actually more information that exists there. Right, so like what part and parcel, what's about this going on here? Part of it is that we have really good references that can be done. So basically, we know things about elemental, that is the so-called atomic scattering factors. So that helps in quantification of this type. And obviously, some parameters come directly from the Bragg relationship, but intensities, have something to do with atomic scattering factors. But there's other things that we learn from this as well. And that is, like we learn things about, like, for example, grain sizes. This is, something that we care about very much. All right. So if I'm analyzing material, part of it's a complex consolidated structure. I might want to know, what's the size of the particles that are diffracting within a sample. I might want to know something about the kinds of strains, like is it an ideal crystal structure, or are the atoms being displaced in some way from what would be their more idealized atomic positions, right? And the thing is that this can be done. Information of this type can be obtained very easily from this type of measurement. Okay, so the advantages of fingerprinting: it's relatively quick, it's easy to do, and it's non-destructive. Okay, and the problem is that it needs reliable standards, and sometimes we're dealing with new compositions and references aren't available, and actually in a number of infamous cases, and this is how my friend Greg Girolami, who is really an incredibly good he's just incredibly good in this area and knows everything about inorganic structures in the solid state. If anybody, if there's one person to ask this question, ask a question about in this space, it's him. He's the first person I go to, and he'll tell you that sometimes the things in the database are rubbish. And if you don't know that, it can lead to horribly embarrassing outcomes, and that happens every now and again. But people are forgiving. Okay, and another thing you have to worry about is the issue of preferred orientations. We saw the example of the single crystal, the large one. If we had a preferred orientation, some reflections go silent. But even in finely dispersed materials, sometimes, like for example, platelet structures, they might lay all flat to first order, and hence we don't see even in the powder spectrum something representative of all the things that would be present in diffraction collected from a mixture from an isotropically averaged set of projections. All right, so let's actually look at this issue of variations from ideal crystallinity. And we talked about for example, strain as one example, but also for example the issue related to the presence of amorphic content. Right, diffraction only reveals the coherent portion, right? The part that is capable of supporting the scattering, the coherent scattering of X-rays by the sample. But sometimes, there's more stuff present in which that's not true, right? And that amorphic content may also be part of the sample. So let's look at the issue of substitutional properties, impacting diffraction patterns, and here's an example of how a difference would be manifested by doing a manipulation of composition in which we do a dilute substitution of magnesium for calcium in the crystalline solid of the calcite structure, right? So calcite is a mineral structure, calcium carbonate, and the reason why these would be different is because the ionic radii of of magnesium and calcium actually differ appreciably. I'm actually surprised that you could substitute this much magnesium for calcium and have it occur substitutionally, because this is really a quite amazingly large difference. So 1 angstrom versus 0.72 angstroms, that is an absolutely huge difference, right? But it does form a solid solution, at least within this range of compositions, and by Vegard's law, the lattice constants for a mixture are actually going to vary in a way that's given by a statistical relationship, related to this mixed composition. So basically, it's just averaging linearly between the limiting unit cell dimensions of the two pure phase components. Okay, and so we would have shifts of peaks that correspond, for example, to these bond strains that come from the substitutional attributes. And if we're doing a search in a database, and we're thinking it's calcium carbonate, in point of fact, we would have the diffraction patterns of calcium carbonate, but the positions, in terms of the angular component would be wrong, right? And hence, we'd have to think about what that actually meant. All right. How about grain size on peak widths and other kinds of features, right? So here's an example of 3 forms of matter being present in what would otherwise be a multi-phase mixture. It could be single component, multi-component, right? And basically, there's a few things we know. For grain sizes less than 100 for small grains, the larger the grain size, the sharper the peak. The smaller the grain size, the broader the peak. And so an example that's given here is that for clay minerals, They're typically fine grain, and the peaks tend to be broad, and grains that are much, much smaller than 1 micron have very broad peaks. Like, for example, if many of you are studying nanomaterials, this is a thing that you would, have to worry about, because things can become sufficiently small, and the structure of the diffraction patterns could be, broadened out in such a way and flattened out in such a way that they actually become an the equivalent of an amorphic background, right? So if you look at this case where we have an A phase, a B phase, and a C phase, they're showing up with very different line widths, and one actually contributing an amorphic background, right? So, these are things that you would be able to analyze within the context of a diffraction experiment. And the broadening seen for small grains, just the fact that you don't have enough, reflections, so it's called the coherence length. This is what they're talking about, to actually specify the diffraction angle accurately. Okay, and of course, the material in amorphous phase can't be quantified. It can be quantified, but it can't be distinguished as to structure. You can quantify it, right? Because we can quantify based on an attribute of how much background and the form of that background that's actually contributed to the diffraction pattern. Right, so here's an example of line width changes in a particular sample, as as modified as a consequence of thermal annealing, right? And you can see that, in point of fact, we have things that kind of look like equivalent diffraction in both cases, but that in point of fact, the lines are much sharper in the annealed sample. So going up to high temperature is actually made this material crystallize into and coarsen grains in such a way that we now have sharp diffraction patterns, which would allow this to be assigned, right? But we can actually take those broadened line shapes and analyze the line widths quantitatively. And this is the application of the Scherer formula, which relates line broadening, right, to a crystallographic, to the size of the crystalline platelet or microcrystal that's actually being examined. Right, and so basically, where what we look at is this this line broadening, right, which we can analyze for the material relative to a standard, and analyze that according to the angular attribute of the reflection, the wavelength. And the other parameter that's in here is actually a constant, right? And this constant is not a constant that's constant for all materials, but it's a so-called shape factor, which varies around unity, sometimes a little bit smaller than unity, sometimes a little bit bigger, but it's something that has to be defined with respect to some understood representative standard. So that means characteristic for the kind of material that you're trying to measure, and basically, you can look at differences, that exists, such as in the earlier slide that I just showed you, and understand, what that was. So here's an example of it. So if I have a polycrystalline sample with lots of fine grains, such as shown in the micrograph, it would actually be pretty hard to say, what the crystal size was, right? Because it's a fairly, complex looking sample. But I could do a diffraction pattern, and if I had certain characteristic broadening, and here's an example that's given for a set of measurements, I could take those numbers and treat them with the Scherer formula, and say that for example, within a sample that looks like this, but based on the broadening of the diffraction peaks, the average crystallite size is of the order of a few hundred angstroms. So that turns out, again, to be, a form of important information that you might be able to glean from a measurement of this type. Now, we mentioned strain, right, in these deviations. So, strain is an important thing, and it can come substitutionally, but it can come from other sources as well. And actually, in some systems, strains are very important because they underpin how materials not only will function, but also, can really fundamentally modify, and I mean modify in profound ways, underlying chemical properties. So it's not just a consequence for mechanics, it's a consequence for everything. So for example, in semiconductors, strain actually changes the energetic characteristics of the material, like in the sense of how electrons and holes propagate in the material. So, strained semiconductors can be used to make transistors, which have, massively modified transport properties. And so, for example, you could use these kinds of effects to make transistors that have, tremendously increased switching speeds, amongst other things. You can actually use it to control the optical and emission, the light emission properties of light emitting diodes, as another example. So, this is kind of a property that is very much important. And in metallurgy, we care about it, like from the point of view that, if I have a certain grain size and I do mechanical working, it changes, and I want to know, what the mechanical working has done. I can look at that, and if I want to know what thermal processing then does to it, I can look at that, and I can do that all within the context of an X-ray measurement, as is shown in the example. And I can say whether or not, the strains that exist are compressive or tensile, as an example. Are they uniform strain, or are they non-uniform strain? And X-ray measurements allow you to do that. And so there's an example that's done for brass from a high strain state, right, and then going to a low strain state, and that just done via the intermediacy of a program of thermal annealing steps done, right, basically to remove those features. And finally, I would note that you could combine both classes of measurements, right, by actually looking at all the reflections within a diffraction pattern, right? Because basically, if you measure, strain as a function of angle, you're also going to measure as well the size of the crystallite as well, right? So you can measure, both size and strain parameters in this class of measurement just by applying the geometric analysis that's shown here on this slide, and so when you do that, right, you can actually say, from the intercept, what the crystallite sizes are, but from the slope also say what micro strains exist within those average crystallites. All right, preferred orientations, right? So remember, for powders, you only identify, from a powder pattern, the reflections that are possible, and we're always assuming that, that there's a random orientation of crystallites, and so when crystals are platy or needle shaped, or non little chunky balls of stuff, they will very frequently tend to consolidate or form powders that have not the kind of anisotropy that you might think, that they'll embed a form of anisotropy that might be not expected. And so, there will be, in those cases, diffraction peaks that are enhanced relative to others, right? And this can actually happen when, samples are subjected to processing. Like, for example, if I form a solid composite, but I do it in a shear field, I might align things as a result of doing it, the net forming by, flowing material in under forms of compression, and so that there's a shear state associated with it, and that might give you a net anisotropy, but that would be a thing that you might want to analyze. And so, right, this is like a an example that shows this, right? Which shows an oriented sample in an anisotropic powder, and basically you notice that there's the anisotropic powder is one that's the the so-called reference for this, and from this intensity mismatch, we could actually say, what is the net orientation of crystallites, within the underlying structure. So again, so from these deviations actually comes a very useful form of information. So you look at the most intense reflection in the here, and that actually implies a very high symmetry of the orientation of smaller crystallites within that experimental sample. So the information of the diffraction pattern, the background, right? The next part, the background tells you if amorphous phases are present. Right? The peak positions give you information about the unit cell size and shape, solid solution composition, strain states. The peak shapes and widths tell you about crystallite size and the forms of uniform and non-uniform strain that might be present. Peak intensities tell you all about the abundance of a material in a mixture, but the caveat being convolved with issues related to preferred orientations, which you got to be careful to make sure you separate that out when we're interpreting intensities. And also intensities tell you where the atoms are located within each of the unit cells, right? Because at the heart of intensity is the issue of the atomic scattering factor, right? Which scales as Z. Right? And systematic absences also give you understandings of underlying symmetries of the crystalline habit. But that's like a higher order thing, which we're not covering in this lecture. And so at that point, you're now ready to go off and drive this car all by yourself, as newly licensed operators of XRD based forms of measurement. And with that, I want to thank you and look forward to seeing you at our next meeting. Thank you.